Okay. Okay. All right. So we'll get started today. We're going to finish up the chapter 13 worksheet and start on the chapter 15 one. Last time what we were doing is we were calculating Vmax and Km from this graph up here, from this top graph up here, right? As a bit of a review here, can someone tell me the Vmax of that top graph there? Is 100, and the answer is pretty simple. Vmax for this enzymatic reaction is simply where the asymptote is, where the line starts flattening out, and in this case it is labeled as 100. So the maximum rate of this enzymatic reaction, for those who need a reminder, this enzymatic reaction is an enzyme that catalyzes this reaction. I tried to use Dr. Hasey's analogy here. There's an apple, there's an enzyme that breaks the apple up into an apple core and apple slices. So, using that as our fake enzymatic reaction here, this is the data plotted for it, the speed of the reaction, which is the rate of the reaction, versus the initial concentration of substrate. In this case, it is the apple. So, last time we calculated, and if you want, you can review the video that was posted. We calculated Vmax is 100. How about Km? What did we find Km? What value? It ended up being 10. And here's how you find Km from this graph up here. You find Km by first finding where half the maximum velocity is. We said the maximum velocity is 100. So half the maximum is 50, which is right here. That is not the value of Km though. The value of Km is the following. You find the half the maximum velocity, you go straight to the right till you hit the graph, and then you go straight down. Whatever value you have here, whatever the x-coordinate is at half the maximum velocity, that is your value of Km. So Km is going to equal to 10 in this case. And the units for Km are the same as the units for substrate, which is molarity, or like micromolar, or whatever concentration unit you'd be given on the exam. So, as you can see, identifying Km is a little bit difficult on this graph here if you don't memorize the rule. Well, it turns out, and this is more likely what you're going to see on the exam, you're going to be given one of these graphs and asked to calculate Vmax and Km from one of these graphs. So I'm going to zoom in a bit. All right. This is a Lineweaver-Burke plot. You don't need to know the equation for Lineweaver-Burke. All you have to know is the following two bits of information, which I will write down here. Okay. All right. So, Lineweaver-Burke plot is a line. And we know for a line that you have this general equation of y equals mx plus b. You can get bits of information out of a line, right? You can get the slope of the line. What is this value here? The y-intercept. And if you do some math, you can also get the x-intercept. For a Lineweaver-Burke plot, it tells you the exact same bits of information that the previous graph did, just in a different form. On the previous graph, which I'll draw up here in the corner, the y-axis was v, or the rate of the reaction, the velocity of the reaction, and the x-axis was substrate concentration. For a Lineweaver-Burke plot, they invert everything so that the y-axis is 1 over v, and the x-axis is 1 over the substrate concentration. That does some mathematical magic to turn a curved-shaped graph into a line-shaped graph. Therefore, we can identify some pretty easily calculated numbers, such as the y-intercept, which you are supposed to know is equal to 1 over v max. So whatever number you get here, that's your y-intercept. You now have the equation to solve for v max. And this one right here, the x-intercept, is going to equal to negative 1 over km. So whatever number you get here, you can plug into the x-intercept, and you now have the equation to solve for km. Okay, so these are the most important values that you would need to get out of a Lineweaver-Burke plot. There's another thing, and you don't really have to calculate this, but visually, if you are given two different lines, I guess I'll label that line A and line B, you may also be asked which one is more efficient, which one is the more efficient enzyme. And it could be 3 lines, 5 lines, whatever. You might be asked which one is the more efficient enzyme. And there's a mathematical explanation for it. I'll simply just give you the quick, easy way is whichever is the flattest line, when you have if you have like 10 lines to choose from, whichever one is the flattest line, the least steep slope, is your most efficient one. So in this case, B is very clearly not as steep as A, so B is going to be more efficient than A. Okay. All right, that's may come up later when we do some chapter 15 questions, but that's what you should take away when you have a bunch of different lines on the Lineweaver-Burke plot. The most efficient one is the flattest one. The least efficient one is the steepest line, okay? All right, so now that you have that information, let's go back to this. All right, what would Vmax be, or how would you calculate Vmax? What intercept are you supposed to look for here? The y-intercept, right? Well, the y-intercept is 0.01, so let me write that out here. 0.01 is going to equal to 1 divided by Vmax, right? You do some algebra. Anyone know what Vmax ends up being? It ends up being 100 again, which is the same answer as in the previous graph. This is the exact same graph, just in Lineweaver-Burke form. So the same answers we got in the first graph should come out to the same answers here, right? In the first graph we said Vmax was 100. Over here we've just confirmed when you calculate Vmax, doing some algebra, you're gonna get Vmax equals 100 here. Well, in the first graph we know that Km equals 10. Let's make sure that Km still equals 10 here. Well, we do so by checking what? Where do we look on this graph in order to help us calculate Km? X-intercept, so we got that as negative 0.1, right? Very clearly, this is the x-intercept right there. That's going to equal to negative 1 divided by Km. We do some math, some algebra, we find out that Km, we have confirmed our answers that Km does end up being 10. Okay, so you may be given multiple different lines, and you may be asked Vmax of line A or Km of line B, okay? So rather than, memorizing this particular line, I suggest memorizing the formulas for Vmax and Km on a Lineweaver-Burke graph. And as you can see, it's actually pretty easy. Any questions on how to calculate Vmax or Km out of a Lineweaver-Burke graph? Okay. All right. So, yes. The Vmax and the Km thing? Okay. So the two formulas you should know when you look at this style of graph here are the following. Actually, do I have it right here? 1 second. The two formulas you should know are these. Okay? That on a line graph, the y-intercept is going to equal to 1 over Vmax. So whatever this number is, you plug it into this formula and you can calculate Vmax. The x-intercept is going to equal this, negative 1 over Km. you plug in the number here and, into the formula, and you can calculate Km algebraically. Okay, so and please do review the video, and you'll see the explanation. All right, so let's move along. All right, make sure it's still recording. It is. Okay. So after calculating Vmax and Km, the scientists are almost done characterizing this new enzyme. In order to submit their new findings, they must report the value of Kcat and another value called catalytic efficiency. The scientists, in their experiment, they used an enzyme concentration of 1 × 10⁻⁵ molar per second, therefore calculate Kcat and catalytic efficiency. So let me write down some stuff real quick, and we'll work on that. So Vmax was 100, Km was 10, enzyme concentration was 1 × 10⁻⁵ molar per second. They want the value of Kcat and efficiency, catalytic efficiency, which I know we broke this up into a bunch of different SI sessions, but if you review the old SI sessions, you'll see that I gave you the formulas for these, so I'll write them again up here. But this is a summary of the problem. We found Vmax and Km in the previous step. We were told that enzyme concentration was this. We must now figure out Kcat and the catalytic efficiency. Review your notes, but you will find that the value of Kcat is going to equal to Vmax divided by the enzyme concentration. Okay, that will end up being the value for Kcat. It's Vmax divided by the enzyme concentration. So in order to solve this, they have to give you the enzyme concentration. Well, we found Vmax in the previous step, and we were told enzyme concentration is 1 × 10⁻⁵. Let's see what this ends up being. You type this into your calculator, 100 divided by 1 × 10⁻⁵, and you end up getting 1 × 10⁻⁷. So this ends up being the value for Kcat. Okay? Any questions on that? So it's, again, this area of the course is memorizing formulas. This is the formula for Kcat. You just have to make sure you got the correct Vmax in the previous step, and you read the enzyme concentration. You plug them into their spots in the formula, like all algebra classes, and you get your number here. Okay? So we'll have to move on into catalytic efficiency. Anyone remember the formula for catalytic efficiency? Not a lot of people studying. Kcat over Km, exactly. The formula for catalytic efficiency is Kcat divided by Km. Well, look at that. We just finished calculating Kcat, so I'm going to plug that in. Divided by Km, which we calculated in the previous problem, divided by 10. So 1 × 10⁷ divided by 10, you plug that into your calculator, you should get an efficiency of 1 × 10⁶. This would be your catalytic efficiency. Okay, so again, two formulas to measure in this part of the course now is Kcat is equal to Vmax over enzyme concentration, and catalytic efficiency, which is equal to Kcat over Km. You do some algebra using the numbers that you were given, and you can very easily get the numbers, the answers here. All right. Now, what does Kcat and catalytic efficiency tell you? Kcat tells you the maximum rate for one enzyme. It's slightly different from Vmax. Vmax was the maximum rate of your total group of enzymes in a reaction. Kcat is the maximum rate for a single enzyme. Okay, it is a number that you can look up in a table for whatever enzyme you're looking at. Catalytic efficiency it's as the name describes, it's how efficient an enzyme is. The technical definition is how fast the enzyme goes when there's very little substrate around, when there's very low substrate concentration. And you can, I bet there's, if I remember right, there's an exact bullet point that describes it that way. But that's what it means, is that catalytic efficiency is how good an enzyme is when there isn't a lot of substrate around. You want as efficient of an enzyme as possible. Okay. And you do so by having as high of a kcat as possible and as low of a km as possible. All right. So that's catalytic efficiency. I'm going to have to move on because the inhibitor stuff might take a little bit of time. So let's assume now a competitive inhibitor and a non-competitive inhibitor were also discovered for this enzyme. Predict approximately what the graphs will look like when each of these inhibitors are added. So what I'm actually going to do is I'm going to do this for Lineweaver-Burke first, because that is more likely what you would see on the exam is what the Lineweaver-Burke graph would look like with the addition of a competitive inhibitor and a non-competitive inhibitor. So that's what I'm going to do. All right. So here's just a rough sketch of our enzyme, apelase, of the Lineweaver-Burke line that we had for it, right? So the question is, how will the line change due to the presence of a competitive inhibitor? Okay. Last SI session, and you can of course watch the video that I posted as well, we talked about the certain features that a competitive inhibitor has. We talked about how a competitive inhibitor, how the inhibitor directly competes for the active site, same as the substrate, meaning the inhibitor binds to the active site of an enzyme. That directly blocks the substrate's ability to bind to the enzyme. It does, and after that, you have to ask yourself, well, what happens to Vmax and Km? Those are, again, I stress this over and over, those are the two most important numerical values you have to answer when you're talking about enzyme kinetics. So when a competitive inhibitor is added, you'll have to review the video, but we actually determined what should happen to Vmax and Km. Does anyone remember what does or doesn't happen to Vmax due to a competitive inhibitor? It remains constant, exactly. So what that means is a competitive inhibitor will not change Vmax. There's a whole biological explanation for that. The short answer is a competitive inhibitor can be beaten if you just increase the substrate concentration. Because of that, Vmax stays constant, and you can review the video on Thursday. Km, does anyone remember what happens to Km due to the addition of a competitive inhibitor? It increases, right? And here's why. So again, earlier, last couple of SI sessions, we stressed the fact that Km is a number that describes how well an enzyme binds to its substrate. A high Km means the enzyme very poorly binds to its substrate, while low Km is a strong binding. Okay? So, a competitive inhibitor is directly interfering with an enzyme's ability to bind to its substrate. It's making it harder for the enzyme to bind to its substrate. Therefore, a competitive inhibitor will cause Km to increase. Okay, now that we have these two facts in our head, we can kind of figure out what the line is going to look like. One, the fact that Vmax stays constant, meaning this new line should have the exact same y-intercept. Does everyone understand why that is? That is, again, because what is the formula for y-intercept? Y-intercept equals what? 1 over Vmax, right? So if the competitive inhibitor doesn't change Vmax, the line representing the competitive inhibitor should have the exact same y-intercept. So I'm going to put a bullet point here to remind myself that that is at least 1 point on the line representing the competitive inhibitor. But what about Km? We did say that Km increases, and I remember that x-intercept tells me something about Km. So Km must affect the x-intercept. The fact that Km increases must affect the x-intercept. It should either go to the right or the left. if you don't understand this next part, I'll give you some example why. But when Km increases on a Lineweaver-Burk graph, it shifts the x-intercept closer to 0, okay? It shifts, when Km increases, it shifts the x-intercept closer to 0. So I'll explain why. Competitive inhibitor. Let's do so with the following example. Remember our alphalase enzyme, it originally had a Km of 10. That means its x-intercept must equal negative 1 over 10, which is negative 0.1. So we'll pretend that this dot right here, the original line had an x-intercept of negative 0.1. But now with our competitively inhibited enzyme, Km is increased. I'm going to make up a number. Let's say it increases all the way to 100. Km is increased all the way to 100. The x-intercept, the new x-intercept from a competitively inhibited enzyme, therefore, negative 1 over 100, which is negative 0.01. Notice that the x-intercept has shifted closer to 0, okay? And that is because when everything is inverted with the Lineweaver-Burk graph, when Km increases, it actually means the x-intercept shifts to 0. You can choose to memorize that the x-intercept shifts to 0, that's fine. Or, if you want to internalize it mathematically, here's an example here of increasing Km and seeing what happens to the x-intercept. Feel free to internalize it whichever way you'd like. Bottom line is, I have now drawn what the line would look like if a competitive inhibitor was included. The summary is that it has the exact same y-intercept because Vmax remained constant, and it has an x-intercept closer to 0 because Km increased. Okay, so this is what it would look like for competitive inhibition. All right, let me check the time. All right. I'm going to do non-competitive inhibition real quick, and then we're going to move on to chapter 15 stuff. All right. All right, let's see what that looks like. So same start. This is our original line. Now, what about non-competitive inhibition? We have to talk about the features of non-competitive inhibition. Non-competitive. You go look at the previous SI session videos and you'll see that we talked about how non-competitive inhibition basically means that the inhibitor goes to what site? Not the active site, but where does it go to instead? The allosteric site. The non-competitive inhibitor goes to an allosteric site. Because of that, the non-competitive inhibitor does not interfere with the enzyme's ability to grab to a substrate, right? The competitive inhibitor got in the way. The competitive inhibitor took up the active site. The enzyme was unable to bind to the substrate. But for a non-competitive inhibitor, because it does not interfere with the enzyme's ability to bind to substrate, Km is going to be constant this time. Because Km was the number that described how well an enzyme binds to its substrate. So, because I know Km is going to be constant for a non-competitive inhibitor line, I know it should have the exact same x-intercept, because x-intercept is equal to negative 1 over Km. If they have the exact same Km, they have the exact same x-intercept. The question is what happens with Vmax? You go look at the notes. Oh, I'll ask this. What happens to Vmax with a non-competitive inhibitor? It decreases, and the reason why is what a non-competitive inhibitor does is it shuts off the enzyme. A competitive inhibitor is just getting in the way. A non-competitive inhibitor is shutting it off. Because of that, Vmax is actually going to go down with a non-competitive inhibitor. So a non-competitive inhibitor, therefore, Vmax should decrease. On this graph here, I know that if Vmax is changing, it's going to affect its y-intercept. When Vmax decreases, the y-intercept actually increases, and we'll give some sample numbers to show an example here. But this line is going to represent your non-competitive inhibitor. All right, so if Vmax decreases, the y-intercept increases. You can choose to memorize that, or if you want to internalize it mathematically, let's do an example here of numbers. We know the original Vmax was 100, right? The original Vmax was 100, which means the y-intercept was 1 over 100, which equals to 0.01. If Vmax decreases, let's say the new Vmax inhibited is, we'll say it's 10 now. We'll say it decreased all the way to 10. What would the new y-intercept be? Let's see, y-intercept equals 1 over 10. It equals 0.1. Notice that the new y-intercept, even though Vmax decreased, notice that the new y-intercept is higher up than the old y-intercept. So that's why, well, I just picked a random spot up here, okay? And again, you can choose to memorize the shapes of these lines and, you know, what they look like compared to the original line. For comparison's sake, you can look at the competitive inhibitor and you see that they should have the same y-intercept, but the competitive inhibitor has an x-intercept closer to 0. And you look at this one here, the non-competitive inhibitor should have the exact same x-intercept, whose y-intercept, though, is a little bit higher up. What can you say about efficiency? Let's start with competitive here. What can you say about efficiency here? Well, remember that efficiency, what's the best way to find efficiency on this graph? The most efficient enzyme. What do you look for? The flattest looking line. Well, look at that. A competitive inhibitor created a very steep line, which makes sense. An inhibitor should not make an enzyme more efficient. An inhibitor is ruining the efficiency of this enzyme, and we see that mathematically as a very steep line. Let's confirm the same thing with a non-competitive inhibitor. With the non-competitive inhibitor, here's our original line. Notice that when we added a non-competitive inhibitor, it made the line steeper also. So we are ruining the efficiency of this enzyme with this inhibitor, which makes sense. An inhibitor is going to interfere with the enzyme's ability to conduct its reaction, so it should be less efficient. All right? All right, so sorry for going through that really quickly. You can watch the video over and over if you'd like, but I'm a little bit behind and we got to jump into chapter 15, all right? Afterwards, I'll take questions if anyone has them. So I'm going to jump to chapter 15 real quick. It's, by the way, when I say 15, I do mean 13b, whatever the title of this PowerPoint here is. 13b and 15, enzymes regulation. All right, So some things that you're going to have to answer on your own, scattered throughout chapter 15, or maybe it's like 1 or 2 PowerPoints. They talk about these drugs here, and they tell you whether they're covalent or non-covalent binding type drugs, whether they're reversible or irreversible, and eventually there's one corner where they talk about inhibition of enzyme COX-1 and COX-2, which are very important enzymes that cause inflammation. So you know how we have aspirin and ibuprofen and all that as pain relievers? That's because they are inhibiting these specific 2 enzymes that cause inflammation and cause pain. So they are somewhere in your notes. I don't remember the exact which one is which. The one thing I will stress, biologically speaking, after you memorize this stuff, is what does it mean by reversible versus irreversible and covalent versus non-covalent? And it is the following. If a drug, and all 90% of drugs, what they do is that they inhibit enzymes. They just inhibit enzymes in some fashion, competitively, non-competitively. It varies depending on the enzyme, but that's the drug's job, is to inhibit an enzyme. They do so via 2 possible methods, and it varies depending on the drug, covalently or non-covalently. What that means is if a drug is binding to its target enzyme covalently, it's binding via a covalent bond. That is irreversible. Covalent association between a drug and its target means that it is an irreversible inhibition. Irreversible. Covalent means irreversible, and that makes sense. A covalent bond is very strong. It is basically irreversible. A non-covalent bond, therefore, is reversible, because a non-covalent bond, that could be like hydrogen bonds, it could be ionic. Well, actually, ionic's not a good example. It could be hydrogen bonds, it could be dipole-dipole, it could be van der Waals, whatever. A non-covalent bond is a weak bond, therefore, a non-covalently binding drug is a reversible binding drug. Okay, so I just wanted to stress those two things for you. The rest you'll have to answer on your own. Same thing here. Enzyme activity depends on many factors. There's two I think we talked about. Temperature, and maybe we didn't talk about pH, but those affect enzyme activity. There's others in chapter 15 that you're just going to have to memorize. So I'll leave that up to you guys. And if you don't find it, you can send me an email, but I'm going to leave that to you guys. This first one here, we answered at a previous SI session. So I'll actually leave that to you guys as well to review the video for it. This question is basically saying a competitive inhibitor is allowed to bind to which of these things here? The free enzyme, does a competitive inhibitor bind to a substrate? Does it bind to a product? Or does it bind to the enzyme substrate complex? Or more than one of these up here? So you can review, or you can either look in the PowerPoint to find the answer to that, or you can review the video from last week. All right, now how about we get to something like this? And this should be easy now that I've given you the shortcut. Given the following graph, determine which enzyme is the most efficient enzyme, assuming the concentration of each enzyme is constant. This used to be a lot harder, but now that you know the shortcut, which one is the most efficient one? It is C, because it is the flattest looking line on here. Okay, so again, efficiency, it is the flattest looking one. How about this one? It is C also. It is the flattest looking line. B and A are steeper, so C in this one is also the most efficient one. How about a second question here? Up here, what if I told you these were all the exact same enzyme, but something was added to A and B? What do you think was added to A and B to cause the line to shift like that? What's that? It is some type of inhibitor. Raise your hand if you say competitive. Raise your hand if you say non-competitive. The answer is that it is a competitive inhibitor. It is affecting Km. And again, you can review your notes. I'll say why. This represents the addition of a competitive inhibitor. Let's pretend C was the regular enzyme, but A and B was adding different amounts of a competitive inhibitor. How do we know that a competitive inhibitor was added? Well, those two properties that we stressed, right? We stressed that a competitive inhibitor, Vmax should be constant, and what should happen to Km? Should increase. Km should increase. On this graph, what that translates to, Vmax being constant means y-intercept is constant, and the x-intercept moves closer to 0. That represents Km increasing. Okay, so this graph represents an addition of a competitive inhibitor, of different amounts of a competitive inhibitor. Well, we know by process of elimination, therefore, that this must represent a non-competitive inhibitor, and we know why that this one's a non-competitive inhibitor. Again, boils down to those two important variables. For a non-competitive inhibitor, Km is constant. So on this graph, that translates to the exact same x-intercept. And for a non-competitive inhibitor, Vmax should decrease, which on this graph translates to the y-intercept increasing, because everything is backwards with the Lineweaver-Burke graph. Okay? So efficiency, again, is just you look for the flattest line in whatever example is given. And in terms of inhibitors, you look at what's going on with the two most important variables, Vmax and Km, to figure out which type of inhibition you have. All right. Now, I'm going to go back to the PowerPoint and get to the more complicated stuff now. All right. So a lot of this is repeating stuff that you see in Chapter 13. So don't worry if you see the same graphs over and over again. They're talking about the same thing. Oh, one vocabulary word, and I guess I did forget to mention it, is something called a suicide inhibitor. all right? A suicide inhibitor is kind of like a secondary category for drugs, for drug inhibitors. What a suicide inhibitor is this. It is a competitive inhibitor that binds irreversibly. All right, I'll say that again. A suicide inhibitor is a competitive inhibitor that binds irreversibly. Meaning what? If it's a competitive inhibitor, where is this thing going to bind to on the enzyme? The active site, right? A competitive inhibitor binds to the active site. So suicide inhibitors are competitive inhibitors. Their extra unique feature, though, is they bind irreversibly, meaning how do they bind to the active site? Covalent or non-covalent? Covalently, right? Irreversible means it's a very strong bond, which basically means a covalent bond, okay? So suicide inhibitors are competitive inhibitors that bind covalently. A good example of a suicide inhibitor is penicillin, which you can find details on penicillin, I think, right here, okay? But I'm going to move on to the following thing is this. So, the main thing with chapter 15 is it tells you the different ways enzyme activities can be regulated. The first way they detail is through something called covalent modification. So you're going to need to know the different ways enzymes are regulated, how their activities are regulated. The very first one is covalent modification, which is this thing here. So let me zoom in a bit. Okay. This one's probably one of the easiest ones to memorize because all covalent modification means is that the enzyme is modified by something. You covalently attach something to the enzyme. The most common example is you covalently attach a phosphate to the enzyme. Covalently. It isn't non-covalently because, and I should stress that because there's a later way to regulate enzymes you're going to learn later where they're doing something with phosphates non-covalently. This is covalent modification where you're covalently attaching a phosphate to an enzyme. Well, where do they get the phosphate from? Well, that's where you get all phosphates from, or most phosphates from. You get it from ATP. So the way this enzyme is regulated is by covalently attaching a phosphate, or the opposite, covalently removing the phosphate. So what does this do to the enzyme? Well, most enzymes, when they have a phosphate attached to them, it actually increases their activity. It either turns it on or makes it go faster. Okay? That's not true 100% of the time. Sometimes you actually have to remove the phosphate to make it go faster, but don't worry, you're not asked to memorize a million enzymes and figure out which ones are turned on with phosphate and which ones are turned off with phosphate. You don't have to worry about that. Bottom line is that covalently modified enzymes, their activity changes by the covalent addition of a phosphate or covalent removal of a phosphate. Well, why could that be? Well, remember way back in chapter 4 and 5 and 6, we learned that proteins have three-dimensional structures, right? But what determines a protein's three-dimensional structure? What did Anfinsen's experiment show? What determined a protein's three-dimensional structure? It's amino acid sequence, right? It's amino acid sequence that has acidic amino acids, basic amino acids, polars, and non-polars, right? Some random combination of that allowed the folding of that amino acid sequence into a three-dimensional structure. So the three-dimensional structure of a protein greatly depends on the overall polarity of these side chains, whether acidics and basics, polars and non-polars. If you covalently attach a phosphate to an enzyme, look at all these negative charges. You are going to mess with that enzyme a lot. You are going to mess with its overall charge and polarity and stability. And that is why the activity of the enzyme changes so dramatically by just covalently attaching a phosphate. Is that look at these negative charges, it's going to change dramatically. For some enzymes, it makes them super active. It turns them on and they go and faster as they could possibly go. And for others, attaching the phosphate might actually turn off the enzyme and it is no longer able to do whatever activity it's supposed to do. Many, many biological reactions depend on this turning on and turning off of enzymes. And this is one of the many ways that the body uses mechanisms to regulate certain biological pathways. In Biochem 2, you'll learn a lot about all those different pathways. If you're studying for the MCAT, you need to be studying those pathways starting now, such as like glycolysis and citric acid cycle and all that. A lot of those enzymes are potentially regulated by covalent modification. Some vocabulary words to attach to this graph here. There are two vocabulary words especially. The phrase converter enzyme and the phrase interconvertible enzyme, which might be down here. The phrase converter and the phrase interconvertible. They mean different things, okay? The phrase converter enzyme is the phrase we use to describe the enzymes that are adding the phosphate and removing the phosphate. We see on the top part of this picture here that the enzyme that attaches a phosphate is called a kinase. In fact, going from this class onwards, whenever you see an enzyme that has the name kinase in it, doesn't matter how long the name of the enzyme is, if it has the name kinase in it, its job is to attach phosphates to something. Okay? The bottom one, the bottom enzyme here is the opposite. It's called phosphatase. Going from this class forward, if you see any enzyme that has the name phosphatase in it, its job is to remove a phosphate from something. Okay? So each of these are converter enzymes because what are they doing? They are attaching or removing a phosphate from a target. They are converting their target, either turning it on or turning it off. So kinase and phosphatase are your converter enzymes. The other vocabulary word, the interconvertible enzyme, is the target enzyme, okay? The interconvertible enzyme are these green boxes here, or is the target, the one actually getting the phosphate or losing the phosphate, is your interconvertible enzyme. It is able to convert from one thing to another. It is interconvertible, all right? That is one thing that a lot of people get mixed up on, so I just wanted to stress that. Converter enzymes are the things doing the conversion. Interconvertible enzymes are the things that are being converted. Okay. Yeah.
So that would just be the enzyme?
Yeah, that would be whatever the target enzyme is, which changes depending on the question. We're going to learn about one called glycogen phosphorylase in a little bit that can be covalently modified. Okay. Good. Any questions on covalent modification? All right. The other type of regulation, so going in order of the PowerPoints, the other type of regulation of enzyme activity is zymogen activation. Zymogen activation, which I'll simplify as the following. All right. We'll use the example that they use in the PowerPoints here. There's an enzyme called insulin, but it isn't made as insulin to start with, to begin with. Insulin is actually in a form called proinsulin, or, you can think of that as pre-insulin. It's insulin that isn't ready yet. What proinsulin is, and I'm going to exaggerate its structure, is this long winding series of peptides put together. Okay? It's a long line, and they're hooked together by covalent bonds at certain places, whatever. That's proinsulin. Active insulin happens when you remove part of this, to where that all you have left is only a part of proinsulin. The remaining part is actually active insulin. Okay? So what zymogen activation means, and I'm sorry I can't really fit all this in one screen, what zymogen activation means is when you have this structure that is the precursor to your actual enzyme. In this case, it's proinsulin, this long structure that doesn't do anything. And activating this via zymogen activation means cutting away, cleaving the parts that you don't need, and what's left behind is active insulin or active enzyme. So that is zymogen activation. And of this, we have 3 examples of zymogen activation. One is this insulin mechanism, where you cleave off this stuff from proinsulin and you end up with active insulin. Let's look at 2 other examples of zymogen activation. Another example is how trypsin and chymotrypsin are actually activated. We recognize those, right? We use these enzymes to figure out how to sequence peptides, right? Well, it turns out that those in the body naturally are activated via zymogen activation. Take a look at this inactive chymotrypsinogen. It's like pre-chymotrypsin. It's this long blue and pink line structure. Through zymogen activation, they remove this pink stuff and you end up with this stuff left over. That is the active form of chymotrypsin. You have cleaved off the stuff that was the useless stuff, and whatever is left behind is the active form of that enzyme. So this is zymogen activation as well. The last example are the enzymes involved in blood clotting. In fact, for this one, it goes through several rounds of cleaving in order to activate it further and further. So there's obviously not a good illustration here, but that's basically what's going on, is that there's a series of zymogen activations. A bunch of, you cut it shorter and shorter and shorter, and it does more and more activity for blood clotting. It's a cascade of zymogen activation here. Okay. Those are your 3 examples of zymogen activation. So far, and we'll have to stop here, so far those are the 2 ways that enzymes are regulated. We will continue next time and start answering some questions on the worksheet. Whoever has the has the sign-in sheet, please bring it up here. And if anyone has any questions, oh yeah, thanks. And if anyone has any questions, I'll stick around for a little bit. Thank you.